In this video lecture, today we will introduce a new concept. Although this concept cannot be physically, formed by an equivalent circuit model, however, it will provide a mathematical tool to, calculate various parameters of the power system. The concept is complex transformer ratio. Practically, any complex transformation ratio cannot exist in nature. However, it is a mathematical tool which will help us to simplify various calculations. Now let us see how to explain this mathematical concept. The concept of this a complex transformer ratio will be used when we will study regulating transformers. Now, there are two kinds of regulating transformers. First one is voltage regulating transformer. And the second type is phase regulating transformer. As we have seen that the reactive power usually depends upon the voltage magnitude. So this kind of transformer is usually used to control the reactive power. And we have also seen that the phase angle usually changes the active power. So this transformer is usually used to control the active power. Okay. So this voltage regulating transformer can be easily explained mathematically using real transformer ratio. However, this phase regulating transformer is usually explained mathematically using complex transformation ratio. Now let us see how. As we have seen that in phasor quantities, let us say a phasor V is represented as V angle theta. What does it mean? It means that its phase is leading by an angle theta and its magnitude is V, and this is the reference phasor at 0 degree angle. Okay, so the angular part or the phase angle part is usually shown in complex form by this angle theta. Now, we should always keep this in mind that usually when we are referring to a phasor, although mathematically it is a complex quantity, however, we usually, if we want to transform it into the time domain, we usually take only the real part. This thing I already covered in my lectures in the very beginning. Okay, so this is Vt, and at a given frequency omega, I can write it as Vm cos omega t plus theta. Okay, so in this way I can easily convert a phasor into time domain and time domain quantity to the phasor domain quantity at a given frequency omega. Okay, now usually we see that transformers are used for changing the voltage magnitude. That is, let us say this is a transformer and here let us say this is the voltage magnitude V1 and this is the voltage magnitude V2. Now let us say it is transformer ratio N1 and it is N2, okay, the number of turns. Now we know that V1 magnitude over V2 magnitude is usually given by this N1 over N2, which is a real quantity, because Magnitudes are real, so its ratio is also a real quantity. Now, what will happen and how will I try to show it mathematically if this transformer is giving some phase modification also. Let us say if this V is the phasor quantity, let us say it is at 0 angle. Now the transformer has also introduced a phase difference, let us say phi. Then how will I show this? Now the transformer ratio V1 over V2, these two are phasor quantities, not the magnitude, can be shown as N1 over N2 angle phi. Okay, now this part, this thing has become a complex quantity. Now it is no more a real quantity. Mathematically, we are trying to represent this transformer which is giving magnitude shift as well as the phase shift through a transformer ratio which is a complex quantity. Okay. Now in the next slide, we will try to first see a basic voltage regulating transformer, then we will try to see a phase regulating transformer. Let us draw a voltage phasor diagram for a three-phase system. Let us say it is VAN, this is VBN, this is VCN, and the angular difference is 120 degree. This is the neutral point, this is A, this is B, this is C. Now the line voltages can be easily drawn as, this is VBC, this is VAB, and this is VCA. Okay. Now we have already seen that a normal transformer usually transform the magnitudes only. So this kind of transformer we have already studied. Now we want to make a phase shifting transformer. You see, instead of adding, let us say I am trying to change the phase angle of this phasor VAN. If I add any quantity or subtract any quantity which is in this direction, that is in the direction of the phasor itself, it will change the magnitude, phase will not be changed. However, if I add or subtract any quantity which is in quadrature or 90 degree angular phase difference like this, then the magnitude will change very marginally, that is very low. However, the phase angle will be changed by a big amount as compared to the magnitude. So if I add in this phasor voltage VAN a quantity which is in the phase of VBC, let us say I add a very small quantity whose magnitude is very small and transformer ratio is, let us say, T times VBC. Now the resulting voltage this is resulting voltage VAN dash. Okay, now you see that the magnitude of these two voltages VAN and VAN dash are quite equal. That is, VAN is approximately equal to VAN dash in the magnitude. However, the angle between these two have changed by quite a big amount as compared to their magnitudes. So from this we have got an idea that to change the phase of any phasor, what we should try to do, we should try to add or subtract a quantity which is in quadrature phase to the original phasor. Okay. Similarly, for this VBN, what should I do? I should add or subtract any quantity which is in phase with VCA, like this. Either I add or subtract. Similarly, for this VCN, I should either add or subtract any quantity which is in phase with VAB. Okay, so if I somehow make a transformer which will do this activity, then I will be very easily changing the phase of the various voltages. So if I try to draw this transformer, what will I do? Let us say that I am trying to change let us say this is the primary, this is A, this is B, this is C, and this is N. A, B, C. Okay, now on the secondary side, I want to get a voltage VAN dash, okay, and VBN dash, and VCN dash. Now I want that this VA dash N is having a phase difference as compared to this VAN, and the magnitude should be quite similar, so that only phase is shifted. What will I do? I will add in this voltage a voltage which is in parallel or in the phase with VBC. So I will make a coil which is magnetically coupled with VBC. Okay, so I will take a coil across whom is a voltage in the multiples of VBC. Now the voltage across these 2 points, A prime and N, will be this voltage VAN prime will be VAN plus TVBC. Okay, similarly for other phases I can do similar thing, that is I will add or subtract any quantity which is in quadrature phase to the original phasor. Now we know that in terms of magnitude VBC is root 3 times of VAN. Okay, so I will substitute these things. VAN prime, this is a phasor quantity, is equal to VAN. Now this is VAN, this is VBC. So I can write that VBC in terms of phase is minus J times VAN in terms of phase only. Okay, and in terms of magnitude, this T is taking that thing in care. So this is minus J T times VAN. So VAN prime is nothing but VAN into 1 minus J T, and this root 3 also is there because VBC is root 3 times VAN. Root 3 VAN T root 3. Okay, now this T is actually very small. You see, this magnitude wise, this thing is very small as compared to 1. Okay, so I can write that VAN prime is approximately equal to VAN angle tangent inverse minus T root 3 or root 3T by 1. Okay, so in this way I have made a transformer which is just shifting the phase of the voltage and the magnitude remains same, VAN. Okay, and the angle is changed by just this amount, which is just minus tangent inverse root 3T, and this phase angle is controllable just by varying this magnitude T. If I just, let us say, increase this T, then phase will change more. So in this way I can control the phase shift. Now this is the concept behind a phase regulating transformer. Now herein I have still not introduced the complex transformation ratio. I will introduce in the next slide. Now, as I already told in the beginning that this phasor quantity, although is a complex quantity, but it is just a mathematical tool only to visualize things and solve them in a very simple way. Now, let us take a transformer which is ideal. Let us say this is current I1 entering the primary and this is voltage V1 across the winding 1. Now let us say this is the second winding. Voltage across this winding is V2 and the current going outside is I2. Now, since I am taking this transformer to be ideal, then there is no real power loss or the reactive power loss. That is, the complex power entering is equal to the complex power leaving. Okay. Now, what is S1? S1 is nothing but V1 I1 conjugate. What is S2? It is nothing but V2 I2 conjugate. Now let us say this is 1:A times transformer ratio transformer. So I can write V2 over V1 is nothing but A times over 1. Okay, or V2 is equal to A V1. Let us say this is equation 1, this is equation 2 and this is equation 3. Now here this A is a complex quantity, that is I am assuming that this transformer is changing the phase of the voltages as well as their magnitudes. Okay, so putting this 3 into 2, what I will get? S2 is equal to AV1 I2 conjugate. Let us say this is equation 4. Now as I already told that this is an ideal transformer, so S1 is equal to S2. So putting equation 1 and 4 as equal, what I will get? V1 I1 conjugate is equal to AV1 I2 conjugate. V1 gets cancelled, so I1 conjugate is equal to AI2 conjugate. Now if I want to take conjugate on both sides, what I will get? I1 is simply equal to A conjugate I2. So these are the two equations. V2 is equal to AV1. This is equation A and this is equation B, where I1 is equal to A conjugate I2. So when the transformer ratio is taken as a complex to solve mathematical equations consisting both the phase difference and the magnitude difference, then we have to take I1 as A conjugate I2 and V2 as AV1, so that this relation is satisfied. Okay, so in the upcoming videos we will assume that the transformation ratio is a complex quantity, and instead of using V1 is equal to V2 by A and I1 is equal to AI2, we will have to change this thing to I1 is equal to A conjugate I2. Since for a real quantity, its conjugate is equal to the quantity itself. So whenever A is real, this equation is same as we have already studied in our previous lectures for a transformer with real transformation ratio. However, whenever this quantity is not real, then this thing might not be equal. So we have to see that we have to use these two equations for voltage and currents. Now in the next slide or the next video, what we will do, we will try to derive the admittance matrix for a transformer which is having complex transformation ratio. Now if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel. Thank you.